That's so dumb.
Should we get started? What's that? No, I did not. I know, that's sad, isn't it? Why didn't I get ice cream? I did eat some good food there, but... Okay. Love the nerd talk, but we gotta get debating Vim versus Emacs, Debian. How y'all doing? I missed you all. Which lab? How'd that go? Okay. I didn't hear any complaints.
I could never figure out how to use the functions that you gave us. There was like the ones for like decrypting and encrypting things were great, but the one for like messages and message type was very. I don't understand. I still don't understand to this day how they actually work.
Okay. That's good to know.
I honestly didn't realize that you gave us message.py until I was on the last step, and I was like, oh, I've been parsing everything myself.
I mean, yeah, you don't have to use it. That's fine. I do encourage you because it kind of helps abstract the message parsing from the rest of the logic.
Which we've been doing.
Yeah. So, and why I give you this? I mean, because this is an opinionated way of doing it. Where is my labs? It's just maybe it would be helpful for your next lab. So just as kind of like this is how I did it. Once again, this is not like the perfect way of doing it, but here's my client. What's going on here? So like you can just go through, where is it? Okay, like I create a message. So first I have to create the socket, and I create the message. So I just say, hey, it's a message of like type hello. There's no payload, so I don't need to do that. So now I have this message, and I call 2 bytes to actually get them. It takes care of serializing. That's what it's called, serializing or marshalling. There's all different terms, but essentially converting it from whatever structure it's in into bytes. So bytes, and then when I receive it, I call message from socket S, and I pass in the socket, which it's going to receive, and it takes care of calling receive as many times as it needs to receive from the socket, putting all the bytes it gets in the right place, and popping out a nice little message for me of a certain type. And then from there I can say, well, make sure it worked, make sure it's the right type, make sure get the, everything like that, get all the stuff I need to from it.
The message equals message dot from socket is what was giving me errors. It was telling me that message was a class.
Yep.
And the classes couldn't be called.
That's a good point. So yeah, if we look at this structure right here, so notice how there's some class methods. So that's key. There's class methods, those can only be called on a class, and then there's some type methods like these that are called on the type. So,
yes, but it wouldn't. I said I got some of Eli's code and he figured out how to do it. And I copied from his code into my code, like messages.from socket, and then passed in my socket, and it gave me errors saying that I couldn't use it that way. Like I couldn't call that function on this class. I was like, but it's a class function. And then I figured out what this class function was. I was like, well, that should be working. Oh well. And at that point, it was already 10 p.m. last night, and so I gave up, and then I copied and pasted your code, and then altered it, and I just made my own function. So used it in that way, which was very helpful.
Okay. Sounds like something messed up in your setup then, because this should work fine. I mean, it compiles for me, it works.
I didn't have problems with it.
Okay.
Thought it was great.
Yeah, so it sounds like it's a Carter problem, which is an important problem. We all want to solve your Carter's problems, but
I've lost some Carter.
But I'd love to. So if you want, I can look at your code and see better what's kind of going on, just so that you don't have that problem in the future. But
something I will say is that I think it would have been nice if there were little comments like this function expects blank, because I literally took your code and gave it to chat and said teach me how to use this. So
okay, fair enough. Yeah.
Constructive feedback.
No, that's good. Yeah, I should probably you're talking comments right here.
Yeah.
I think adding annotating what class.
Yeah, just data types that it's expecting.
Like that socket, I guess, would be socket.socket, and then if you go to the cryptograph.
Oh, okay, crypto. I don't want to make it too easy for you guys. It's not like a well-documented library.
I mean, libraries do document what.
This is not a library. This is just a little bit of helpful stuff for you. Okay, maybe it should be a library. I don't know. I guess I'm not ready to commit to making it super well documented.
You have to start maintaining
I want to make you guys have to work a little bit for it, because other than that, like, what's the point of the lab? Like, the lab is just then like just this part right here, which simple as
Only
Dr. Luck, before class, we're talking about how you should make your future students do full TLS clients because of how simple this one was.
noted. Okay. Just future, yeah. Okay. Anyone started working on the new lab? Good. Have you guys watched the video?
Downloaded the repository, which is bare bones empty.
I don't think it's empty. Yeah, I think there's nothing in it. Okay.
I accepted the assignment for the other lab.
Last day of class. Yeah, that's right.
But it does take an
That's
average
gonna
of 15
take
to
a
20
long
hours.
It's a long one, so yeah, I would work on that sooner rather than later.
I have actually a question about it real quick.
Sure.
So for the client, like when you're acting as a peer client and you connect to another peer to ask for stuff,
Yep.
do you connect and then ask for every single piece you're missing from them and then close the connection, or you ask and download one piece, cut off, and then ask it reconnect again?
I leave that up to you.
So there's a-
I don't think it matters. I think you should. I mean, this is the fun of it. I guess of like, the server should handle either one. So the other peer, but other peers might not actually handle it. I don't think you should close every single time. That's just, people have done that, and it takes way longer, because now you have to do a three-way handshake plus request plus response, three-way handshake. That's, the difference between persistent HTTP and non-persistent HTTP, right? So I would suggest you don't close connection, but someone like one of your peers, literally your peers, might only build their server such they can only handle that. So that'd be kind of fun to figure out. That's actually that I was saying I was talking to Ashton. Ashton, was the TA last year. He was with me on this trip. He said one of the hardest parts of this lab, which I like it, I think, is that you guys are going to be interacting with other peers. Like, someone might have uploader that you're trying to download from, and they might not have implemented the protocol perfectly right, and you might crash. And so you need to write your code really robust. I mean, that actually happened to me. That's an experience I had in a similar class. And I was so numb, like, this guy wrote the wrong code, I'm mad at him, and I realized I was the one with the bug. And so it's kind of a humbling experience to interact with other people's code and see whose bug it is. So yeah, good luck. So to answer your question, I don't think you should close the connection. You should be able to do other requests, but you're gonna be interacting with other people's code. So make sure you write good code, make sure you handle all exceptions, and what is it? What's the saying? And clients should be as strict as possible, and servers should be as gracious as possible. I don't know. That's a more poetic way of saying, like, on the internet, your server should be like taking anything it can and just like try to make sense of it as best it can. But a client should be very strict and rigid, because like you're wanting to implement the protocol as well as possible as a client, but servers should allow for lots of different types of clients, ideally. Okay, any other questions on that? Okay, start working on it.
Is this going to have an auto grader as well?
No.
Yeah, how's this going to be? Yeah, like
So I said before,
It's gonna take you.
you're going to post a video recording it functioning properly.
Hey chat, make this video.
Let's feel this out. This is a new thing. So record a video, or would it be better to pass off to Bryson? Would you prefer that, having a person in the loop?
Probably
Pass-
video, so you
I
don't have
don't
to coordinate.
Yeah, Bryson's never gonna be available.
I
I'm
think
available and trying to pass off.
if both would be available, like
Yeah,
if
we
you
do
aren't,
either or.
if you aren't able to pass it off with Bryson, then you would create a video.
How about we just do this? I look you in the eyes and say, I will do the lab. And then you put it in the-
Perfect. We can do a handshake.
Yeah,
and-
we can handshake.
Okay.
Shake on you on the final.
What's that?
I will get an A on the final.
Because I don't really want to watch a bunch of videos, but I don't know.
Torture Bryson.
Yeah, you
But-
can make him watch.
But like,
Yeah.
yeah, if you're willing to let us pass off with you or Bryson,
Yeah.
but then if the deadline comes and we have to make a video, then
Okay. We can do that. Trifecta, the Triforce.
just to
Okay.
prevent you from having to watch videos.
Okay. I'll allow that.
I think it's only like, what, 25, 30 videos?
33.
Half of it 30 seconds.
Okay, so you would need to demonstrate to me what it means it working. So what that means, I mean, you guys haven't even worked on the lab, so you're not going to know what I'm even saying. But for some people that have worked on the lab, you need to demonstrate that you can download a whole file and you can upload a whole file. Yeah, that's it, I guess. and find peers, but to upload files, you need to have found peers and download. So those are the 3 things I'm looking for. Make sure your tracker is working properly, make sure your upload is working properly, make sure your download is working properly. So that'll make sense when you start working on that. Okay, cool. Anything else? How'd it go? So you watched the 2 recorded lectures on Monday and Friday, right? You look me in the eye and tell me you did?
I did not.
Ah, okay.
I
Well, thank-
did watch the 2 lectures actually.
Okay, well, watch them. Repent and watch them at 3 times speed.
Max, you guys on YouTube.
YouTube doesn't support 3x.
There's got to be a plugin that lets you do that or something.
Probably.
Download the video and then re-up at 2x. Screen record at 2x, re-upload. So
Nice.
do
Okay.
2x again.
Put a Subway Surfers right next to it.
Subway Surfers gameplay.
Okay,
GTA, like.
and then how did it go with Bryson on Wednesday?
We read some Shakespeare, it was great.
That's what I heard. He was very excited about that. Did it go well?
Yeah.
You did have a talking stick at one point, or tried to at least.
A talking stick? Oh,
I think
okay.
we tried and failed to implement it.
So you guys learned about what? Mac protocols, right? Multiple access protocols?
Yes.
Mac, okay. What are the different Mac protocols you discussed and learned about? I want to know how much I need to review or how much it was.
It's hard to remember the names.
Okay, fair enough, fair enough. Anyone want to come up with ideas? Like,
There were like 4.
that's about right.
Two versions of a sucky one, 2 versions of a good one.
Let's go.
Not-
Slaughter
yes,
Aloha.
Aloha.
Yep.
Those ones sucked, he said. They're
Oh.
very bad.
Don't, no, that's not true. It just depends on what you're doing. There's no bad Mac protocol. It's just bad applications of the Mac protocol, right? For some applications, Aloha's not good. Others, like LoRa, I don't know anyone use LoRa in this class. LoRa, long range wireless protocol. LoRa uses Aloha, and that's a very successful protocol. It's just if you're only transmitting once a year, then it's a perfect protocol for that because it's super simple. But if you're Wi-Fi and transmitting gigabits per second, then it's not going to be a very good protocol. So depends on what you're doing. So Aloha's, it's not great in the face of lots of nodes wanting to transmit all the time. Then it sucks. I agree with that. Mac protocols all have to do with how do we deal with collisions? How do we avoid them the best way possible? So it's distributed algorithms. John?
So does the MAC and MAC address also
Yep.
stand for multiple access?
Yeah.
Channel
Multiple access control.
control?
Yeah. Or medium access control. I'm never sure which one. And in this case, we're talking about multiple access. But I've also seen it been medium, like the medium in which we're transmitting. Okay. Hopefully, did you go through these slides? Okay. You guess?
Yes.
Oh, yes, okay. So these are the important ones to remember, it's all important, but these are the 3 types of protocols. So channel partitioning, so what does that look like, channel partitioning?
Either frequency or time you pick, and then only one of the nodes can transmit at that.
Very good. So you take some resource, whether it's time, whether it's frequency. Another resource might be space. That's a new thing where I can transmit over here, but I can also be transmitting over here if I have good directional antennas. That way I can be transmitting at the same time, but I'm using space as my partitioning of what I'm partitioning. There's also code division multiple access where you actually use math to be able to transmit at the same time, but they're orthogonal to each other just on how you set up the codes. It's really cool. So you take some resource and you partition it some way. And what are the benefits, pros and cons to this? Gotta go this quick.
You don't have to worry about.
You shouldn't have collisions if it's not the rules.
Very good, yep. So no collisions, that's good. What's bad about it? Complex.
Taking turns isn't fun.
Yeah. Scaling becomes an issue. If you have lots of nodes coming and going, then how do you repartition things? If you have a set amount of nodes, then it's great. But if you have lots of nodes coming and going, then it can be a problem. Okay, then we move to random access. This is where most of our wireless protocols live. No. They actually do a combination of a bunch of these things, by the way. I don't know, did Bryson say that? You can mix and match these. You can say, let me do random access, but partition into different channels, and within each channel do random access. Or I can have turn taking, but then also have a part of my time where we do random access. So you can mix and match all these different things together. Random access, that's aloha. I just go ahead and transmit, and hopefully I don't collide. If I do, I retransmit at a random time. What's another random access protocol? CSMA, does that ring a bell? Carrier sensing multiple access. That's where I listen before I transmit. That's what Wi-Fi uses, that's what Ethernet uses, that's what other protocols use. So that's a really popular one. That's good because it really handles bursts really well. Because what if I'm partitioning the channel between all of us, but let's say some of you don't have anything to say. Like I have lots to say because I'm teaching the class. Maybe you don't have a lot to say. It would be annoying to have to partition it. Everyone has a turn to talk and then gets back to me. Like it'd be really slow. Random access solves that problem where you only insert yourself if you have something to say. So if you want to stay quiet, then you're not taking up any additional time or any resource. You're just only using the resource when you need it. So it's really good for bursty traffic, which is what internet and Wi-Fi traffic tends to be, bursty. The last one, taking turns. That's where you have some kind of coordinating node that somehow passes something around, like a talking stick, the token ring passing, or there's lots of different ways of doing that. So that's kind of supposed to be a hybrid of some of these things where you have one coordinating node. Okay. You feel good about that? Hopefully that was all just reviewing you all already. If not, here it is. Okay, don't blink, don't blink. Collisions can still happen. That's actually worth talking about for a second. You might think, look, like, oh, CSMA, just listen before we transmit. Then there should never be collisions. But the answer, there still could be a collision. We see this all the time with Zoom, right? Where you both start talking at the same time. That can happen. You can transmit, even not at the same time, but it takes time for these waves to propagate. So at time 0, one person might be transmitting, but at time 1, another person might be transmitting it. As long as it hasn't reached that person's signal, they don't know. They might listen and say, oh, no one's transmitting, no one's talking, and they might start talking. So that happens all the time with Zoom when the latency of your phone call is really bad, right? Where there's a long gap between when they start talking when you hear them. Same thing with wireless networks, or just any network, sorry, not just wireless. So this is bad. We don't want 2 people transmitting at the same time. This is just wasted time. So CSMA just doesn't say anything how to deal with that use case. It just says, okay, we're going to collide. So then there's, in addition to it, CSMA CD for collision detection. Some instances, like Ethernet, can detect that there's a collision happening, because Ethernet can be sending and receiving at the same time. So if I'm sending and then all of a sudden I get something on my line, like, wait, that means there's a collision somewhere, then it can abort early. Say, oh, okay, well, there's a collision. Why even am I still talking? Because it's going to collide. I'll just stop right now and just restart. And so that saves time. Wi-Fi doesn't have that luxury, so it uses CSMA CA, collision avoidance. Take my grad class if you're interested in that. Okay, cool. Taking turns, like talked about that. You got some kind of polling here, or some kind of ring with token passing. What's the problem with these, guys?
If every node doesn't have something to send, then it takes up time.
Yeah, it takes up time. Not as bad as partitioning the channel, but there's still overhead and latency.
And single point of failure.
Yeah, what if that token gets lost? Then that's annoying. Okay. And here's an example of you can actually do multiple. Cable TV does multiple. They have different channels that they partition for frequency and time. That's why, like, if you have Comcast, typically your upload is much slower than your download. Anyone seen that? You know what I'm talking about when I say that? Of your internet speed? Because I don't know what.
Upload faster.
Sorry, did I say that wrong way? Your download's faster than your upload. Okay, sorry, maybe I said it reverse. Your download is faster than your upload. Like, oh, I have 100 megabits per second of download, but only like 5 megabits of upload. That's common. It's because they've decided, Comcast or whoever, say, well, like, most people download stuff. Uploading is not as common, so let's partition the frequency so we give actually more allocation to that download stream and then less for the upload. But another weakness of cable, which comes with the time division, is if a lot of people are using the internet, your actual internet will slow down as a result, because you're using time division multiple access. So if you want to transmit and everyone else wants to transmit, you have to wait and take turns. So one of the many weaknesses of cable internet, fiber doesn't usually have these problems. Usually it's symmetric, upload and download, and then usually you have your own independent channel. Okay. Cool. Any questions on that? Okay. Let's get going. So today we're going to be talking about, oh, not VLANs. Sorry, I should have crossed that out. But these three things right here, it should be probably perfect amount of time. I thought early, but now it's 20 after. So let's talk about addressing. So we're familiar with our IP addresses, right? Dot notation, 32 bits. You should feel really comfortable with this, right? That's done for the network layer, layer 3. What about the link layer? So now we're deep into the link layer. What does the link layer use for its addressing scheme? Because IP, that's a layer above, so it knows nothing about IP addresses. Doesn't care about IP addresses. It uses MAC addresses. These are addresses that are part of your hardware. That they used to call it burned into your hardware. They're 48-bit MAC addresses, so a little bit bigger than IP addresses, and they're written differently. I'll show you in a second. But they're different than IP addresses. I guess here's what they look like. Often they have a dash or a colon notation, and they're written in hex. I don't know why they write like this, whereas IP addresses, they write like that. It's kind of helpful, I guess, to distinguish visually. But this is the notation. Remember, it's bytes at the end of the day, so it doesn't really matter how you write it. But these addresses are only meant for local one-hop communication. So like, Google doesn't know my MAC address because by the time it gets to Google, it's long gone my MAC address. My only MAC address is contained from one hop, from my laptop to the access point. And then once the access point gets it and it sends it onto a router, it's going to put its MAC address in there. So it's only for local delivery, these MAC addresses. So here, oh yeah?
Sorry, but just again, what does MAC stand for?
Multiple access control.
Okay, and that's different from like the Mac that we were using in this last lab?
Yes.
Okay.
I try to confuse you guys as much as possible. No, it's not me. It's yeah, but it is different, MAC. So MAC, in this context of security, is a message authentication code that helps protect you from people messing with your data, changing the data. MACs here is multiple access control, so it's the link layer addressing and the link layer stuff. Thank you for clarifying that. Two different MACs. I teach you those things on purpose, by the way, because how I would actually normally do it, call it a MIC for the security stuff, but TLS uses MAC terminology, and so I wanted to help you guys be familiar with that. But MIC, message integrity code, is to help distinguish those, is usually better.
So this is larger than the IP addresses.
Yep.
But I imagine that there's probably a similar issue of where we have a lot of devices now, and all the MAC addresses are probably being used up. Or rather, but it seems like it is less important that everybody has a completely unique MAC address than it would be the IP address.
Yeah.
So are there times when manufacturers are just lazy and give everybody the same MAC address, and then that causes issues? Or
That
how do
would
you
cause
manage
insane issues.
Yeah, I've never seen that. That would be really a big problem.
It's more of an issue to have duplicate MAC addresses than IP addresses.
Well, internet, like, if I'm making, if you have two of the same MAC address in the same household, then yes. But if the two things with the same MAC address exist in the world, it'll be fine as long as they're not on the same site.
I know there is MAC address reuse, that you can retire MAC addresses, so there is reuse in that way. I mean, 2 to the power of 48 is quite a big number. I don't think.
1 trillion.
So that's pretty big. I mean, but it's not as a big concern, and I'm not quite sure why. Because if you did have 2 MAC addresses in the 2 devices with the same MAC address, that'd be really bad. But no one seems to be concerned. I've never heard about anyone worry about running out. I think because you're right, because it's so local that for that generation of devices, I don't know, like for devices 10 years ago that are retired, I don't think you can just reuse those again. I think, but.
So our MAC address is static, like the second that my iPhone has a MAC address, that's set forever?
Yes and no. It's gone a little bit more fuzzy. It used to be, we'd call it, like I said, burned in. Do I have that somewhere in here?
Yes, it was the previous slide.
Okay, did I put that in there? Yeah, it was like burned into the, like, burning meaning like it's physically there, stamped in place. But now it's gotten a little more fuzzy. Now you can actually, most software, and this is always true, you can actually set it in software. So if you want to do malicious things, you could potentially set it to someone else's MAC address, or if you didn't want someone to track you. But then there's been this cat and mouse game where when you connect to a Wi-Fi network, now they know your MAC address. And so if I own a multinational, a big chain, I can start locating you throughout my stores because I have free Wi-Fi. And so if I run Starbucks, I can say, oh, AJ's at Starbucks today. He was there for a couple hours. Oh, now he's in this at Starbucks. Okay, I can start selling him and training on his information. And so Apple and Google have now had MAC address randomization when you connect to an open Wi-Fi network. So then it's kind of violating this whole like, oh, it's hard burned into your hardware. So it's gotten less and less like that. Now it's kind of become a more temporary ID. But it used to be like I would never want to show anyone my MAC address because that would be bad because I can't change it. But now I feel a little less concerned about that. Great question. Any other questions on that? Yeah?
So does that mean MAC addresses used to be like fixed, well, IP addresses would change based on your location, but now they both change?
Yeah, but in different ways, but yeah, they both change. So I know there's another slide I have here. Yeah, analogy is kind of, your MAC address might be like your social security number. And that is something you want to protect, right? You don't want to just like tell everyone your social security number. Obviously you have to give it to some people sometimes. Whereas your IP address is like your postal address. You move to different places, you get new IP addresses every time you move, but your MAC address is something like who you are as a person. It's like your identity of who you are. But to continue with the analogy, it's almost as if the United States said, oh, let's have like rolling MAC social security numbers for every employer you have. You give them a different social security number for privacy reasons. Analogy's breaking down a little bit, but so you should think of for now and for this discussion, think of MAC addresses like social security numbers, where when it gets created, you get a MAC address. When you were born, you got a social security number, whereas your IP addresses are something that's changing. Also, IP addresses encode location, kind of like your postal code. So, oh, okay, you're here, you live in Salt Lake City, you live in Provo. It kind of tells you where you're at. Same thing with IP addresses, right? They encode information about where you're at in the world. But MAC addresses, like social security numbers, actually don't encode any information. Except I think they do, but like where you're born, I think. But
So in the context of this example, IP addresses, we need them because it gives our location. For MAC addresses, why do we need them?
to uniquely identify us on a LAN, a local area network.
Because IP addresses don't do that?
They can, but they come and go. You can get DHCP, you could get different MAC addresses, but we need it for also the layer below IP addresses. What about the link layer? It needs some addressing scheme. So what does it use? So let's go back a little bit and talk about that and hopefully fill this in because we're kind of getting to this. Okay, so we're at this right here. So here, I'm connected to some LAN, wireless or wired, doesn't really matter. I have an IP address because I'm connected to a router, but I also have a MAC address as well. So you'll often have both of those things. Oh, you'll always have a MAC address. You'll likely have an IP address if you're using the internet or a network. It's administered by IEEE, interestingly enough. Manufacturers do own spaces of MAC addresses. So I don't know if you've ever seen Wireshark. Is this going to work? Is Wireshark working for me? Remind me later. So if I go to like my Wi-Fi interface and I start poking around here, notice, come on, and then stop here and then go to like Ethernet. So like, how is it putting this? So I don't know if you've ever seen this notation. It's putting the last 3 bytes of my MAC address, but then it's putting this right here. This is my whole MAC address, or the source of whoever. This is not mine, but someone else's. I'm gonna take a picture. It's actually not mine because so this is because this company, Arista Network, owns these first 3 bytes of data. So that's how it's able to. There's a database that has these in here, and so it maps it.
Does ICANN hold on to that?
No, I think IEEE.
Oh,
Yeah, it's IEEE. So, and like Apple has them. Anyone that makes these devices will own or pay some money to have this. So this is their bytes of data. So that's how it's able to substitute that out. So it's a lot more helpful. Like this is easier to read or help to remember than other devices. Okay. That's how they buy a portion. It's unique to them. Postal code, okay. MAC addresses have a flat hierarchy, in that there's no information about it, whereas IP addresses had not a flat hierarchy. It had a hierarchy to it, right? That's why you did longest prefix matching, because the more left you go, you get into more deeper subnets, right, from left to right. So, okay, there's this subnet that goes deeper into a subnet. There's hierarchy to that. MAC addresses, it's besides those first 3 bytes of what the MAC address of that company is that made your adapter, the rest is just random. Okay?
MAC addresses are based more on the device itself.
Yes, the device itself. Yeah.
So each device has its MAC that it carries with it.
Yep. Yep. Yeah.
So then, does the device have to tell the network it's the local network it's MAC when it connects?
Yes, so we're about to get to that. Great question.
I was gonna say, if the MAC address is only like local, it's one hop, why is it so important to keep it so secure? Because if it's like, it's not gonna go past the next hop.
If we're all connected to the same router, though, that's one hop, right? And so if you knew it, then you could, in theory, trick the network into sending my traffic to you, because you could spoof my MAC address and then convince the router that I'm really,
This is
Phil's
just
laptop.
Protection against adversaries on the same.
Yeah, on the same networks, which is limited in that, like,
Yeah.
you have to physically be present. You're exactly right. That's a good point.
Also, for tracking, like he was saying before, if they identify like your MAC address, then the information that they send to you could be specifically
But
used to track.
to the point, though, you have to be on that same network, though, to some degree, listing in or own the network and be, like, I couldn't be at home, and if I knew AJ's MAC address, I couldn't be like, oh, I'm tracking AJ, like, because I'm not on campus, or I'm not at your home network. I don't know, like, I don't have access to those. Not yet, at least. I don't have access. I'm just kidding.
Big plan.
Got big plans. So yes, how do we map? We've got these 2 different worlds. We got link layer MAC addresses and IP addresses. How do we map between those different things? And that's done through ARP, Address Resolution Protocol, ARP. Often you have an IP address, and you want to say, well, what MAC address do I send this to? And this is what ARP does. So why would you have an IP address? Like what? Like I feel like that's maybe unintuitive. You might think you're going to start with lower, you'd have a MAC address, and you have to resolve to an IP address. But it's actually, you're usually going down the network stack of saying, well, I have this IP address, but great. Well, what device do I actually send it to on the link layer? So why would you have an IP address and not a MAC address?
IP addresses follow a hierarchy, so you can always find where something is, like, from wherever in the world.
Okay.
And you don't have to know the specific, like as long as it'll be able to route it correctly, because you have the first little bit, and it'll be like, oh, okay.
Yeah.
Found the first bit.
Okay. It's very good. I like that. Interesting.
When you're saying you have an IP address, who are you?
Like I have this.
Are you an end user? Or
Yeah,
a
yeah,
router?
yeah. End user. So end user, I have some data and I want to send it to an IP address, and then I say, okay, well, what's the MAC address that I send it to?
Yeah, I guess because if you're an end user, isn't the whole point that you're not supposed to know anyone's MAC address?
Yeah, good point. Yeah, so you're not supposed to know it. Things like DNS help you solve that, right? That'll give you a host name to IP address. Great, I have a IP address, but how do I then send that further down? DHCP also gives you IP addresses, not MAC addresses, so you might need to do this mapping here. So how do you map that? So it's actually a pretty simple protocol, but everyone has an ARP table, so we locally cache ARP requests, and all we do is just we send out, okay, I guess it's got time to live, so this is hopefully feeling kind of similar to DNS, that we have this mapping, but it's IP address to MAC address, and then we got time to live, because maybe someone's MAC address changes. You don't want to have that stored forever, so you have some time to live, typically 20 minutes. So let's say A wants to send to B. Somehow A has B's IP address, not MAC address. So we'll say, hey, who has this IP address? Send, respond to me. Of course, it doesn't know who to send this to. It has to broadcast it out. ARP is a link layer protocol, so it only has to fill out the destination MAC address. So all Fs, what is all Fs? Everyone, broadcast. So it just says, hey, everyone, who has this IP address? then hopefully B will respond and say, oh, that's me, I got it. And then responds back, this is my IP address and this is my MAC address. And then from now on, A can store that entry in A's table. And so if A ever needs to send to B again, it'll look this up for the duration of the time to live and then just map it. And then once this time to live is over, it will then do that same process again. So, yeah.
Does the time to live not update with like successful communication?
I'm not sure. You're saying like every time it does, it would like re-update? I actually don't know. That's a good question. So this is where we get into like ARP poisoning. So that's a terminology where if I was an adversary D, if I could intercept A's communication or respond faster than B in that ARP request, then I could convince A I'm actually B. And then I could potentially do like a person-in-the-middle attack, right? Where I could then relay from D to back to B, or I could do all sorts of stuff. So ARP poisoning or ARP spoofing is another term, is an important, big issue. Of course, you have to be local in the network, so it's limited on who can have access to that network. But that's something you want to be careful about is ARP poisoning. Any questions on ARP? So it's a pretty simple protocol. Just broadcast out, hey, who has this IP address? And someone responds, says, here's my MAC address, and you store it in your ARP table. Okay. So let's go through an example of, okay, that's for one subnet though. What if A and B are on different subnets? They're through a router. Now let's talk about that. So A wants to send to B, but now there's this router between. All this stuff before in the previous one was actually where there was some other device. We're keeping it blank on purpose. We'll talk about it in a second. A switch is what it's called. But with a router, because what is a router? A router works with layer 3, with the IP layer. So it kind of partitions our LAN then in a way, in that now this is all layer, this would be all done at the link layer, but now we get to the IP layer here. So it's going to separate those things out. Okay, so A wants to send to B. Let's assume that A knows B's IP address. How would it know it? It's given to it. Maybe you're told, oh, hey, go to ecn426.ua.edu, and that's just happens to be this when you're on the same network. So somehow you know the IP address. That's common to know the IP address, or at least the network name. You also need to know your first hop router. 'Cause if you say, hey, IP address, send to all twos, 222, I guess. I don't know how to route that. I don't know how to get there. So there's always a first hop router. If there's ever an IP address that I don't know how to send to or send it to, I will send it to my first hop router. So that's pretty much all internet traffic, unless it's like local. I'm sending to you. My laptop will send it to the router by default. So we need to know the IP address of the first hop router. How do we know that?
When we set up a connection with the network, and we send out our all ones IP address, we're like, hey, give us an IP address. The thing that responds to us is going to be our first hop router.
DHCP, right? Is that
Yeah, the DHCP.
So either we have to program it in statically, that's one option, that's not great, but DHCP is, kind of answer. Your DHCP server doesn't actually have to be your first hop router, they can be separate, like at home it's the same device, but your DHCP response will tell you who the first hop router is. It doesn't have to, but that's just a nice thing so that you have to do less work on your end to configure the network. How do you know ours MAC address?
Do you ask for your first hop router with the broadcast?
So it could be done through DHCP or ARP, right? Because I get this, and I say, okay, let me send an ARP request. I now know the IP address of it, this right here. Hey, who has this IP address? And it'll respond back, well, here's my MAC address. So this would be done through ARP.
So is that saying that it has a different MAC address for the different
Oh, I'm
sites?
sorry, I pointed the wrong one, sorry, right here. Yes. Routers have different IP addresses for what interface you're talking to, sorry, I was pointing the wrong one. This is this subnet right here. So I would say, hey, who has this IP address? I know this IP address because of DHCP, and then it would give me this MAC address back. So now I know that MAC address when I send it. So what I'll do is I'll fill in my source IP address, that's me. I'll send my destination IP address, that's who I want to send to, B, so from end to end. Because remember, IP works end to end, but what am I going to put in the Ethernet frame? The source MAC address will be my MAC address, but the destination MAC address won't be this MAC address, because this, I don't know what this MAC address is. That's so far away, that's a whole other network away. Remember, MAC addresses only work locally on that one network. So I will say the MAC address actually is going to the router. And this is why we need both addresses, because my IP address, the IP address I'm filling in here is the end node, but there's lots of hops along the way, and how do I actually get to that end node? So I say, put the MAC address of my next hop router. So this right here. So that's who I'm gonna put the MAC address. So when I send that out, the router will receive this. Yeah, I mean, let's go do that, guys. So it'll receive this. It'll say, oh yeah, that's for me. So it'll pop off the Ethernet frame, and then it'll look at the IP frame, IP datagram, and say, okay, oh, 2, all twos. I know how to get to that. That goes out of this interface right here. And what it will do is it'll create an Ethernet frame. It will put its MAC address as a source MAC address. And now, since they're on the same network, it will put the MAC address of B on there as well. How does it know MAC address of B? Maybe through ARP. Had to say, oh wait, who has, I know that this device is on my network, but I don't know its MAC address. So let me do an ARP request to get that MAC address so I can fill it in. So then it sends it to B. The Ethernet frame, it looks at the Ethernet frame, so yep, that's for me, that's my MAC address, pops it off, passes it up to the IP layer, and says, okay, yeah, that's my IP address, cool, and then passes it up. So now we have 3 identifiers. We have port number. Port number maps to a specific application on my computer. IP address maps to my computer, and then MAC address also points to my computer.
How long does it take you to make these cool visuals?
I didn't make them. But I'm sure a long time. Okay, any questions on that? So that's ARP, that's routing stuff through the network. Next lecture, we'll go over like the whole stack and show from like one packet, and that might be helpful to put all these pieces together. I know we've been talking about all these pieces kind of at different times. I mean, we have been going top, bottom, but it'd be nice like to start with like, hey, you send set a web request, HTTP request. Okay, you have to do DNS, and then you have to do HTTP, and then you have to do ARP, and then like kind of going through that whole process of filling out that packet and then sending it. So we'll be doing that in a future lecture to kind of put it all together. Let's talk about Ethernet. Let's do that pretty oh crap, yeah, we gotta do it really quick. Maybe we'll skip over it actually. Yeah, we'll skip over it. You reading all this? Okay, good. Okay, cool, that's Ethernet. Good job. Let's go to switches. I think we'll end on that. So in this class, we'll be very specific of a router versus a switch. Those are 2 different devices. A router works on layer 3, works on IP addresses. So remember that. Switches work on layer 2, on MAC addresses. There are violations of that. You can buy a switch that does a little bit of IP stuff, or you can buy routers that do a little bit of MAC address stuff, but that's, that's the real world. For this class, we'll just say switches. If I say switch, what should you be thinking? Layer 2, MAC addresses. When I say router, what should you be thinking? IP layer 3. Okay, good. So be thinking about that, and I will try to trick you. I should try. I'll test you on that knowledge. How about that? So it's, what's that? Whatever else you sleep at night. Fair enough. So how do these switches work is kind of what we want to answer here. They are active devices. They're not just like passing electricity. They're actually looking at the packets and understanding them and forwarding them to different nodes. So let's go through. But what's cool about them, they are transparent to the user. They don't know that a switch exists. Kind of like a power strip, right? In that, like, I plug in a device, another device, like those devices don't know, oh, I'm sharing my power. It's like I got my electricity from a switch, like, or from like a power strip. Same thing, like if I plug in an Ethernet switch, my computer doesn't know that it's somehow a switch is connected up to it. It's completely transparent to that device. And they're plug and play self-learning, which is kind of cool. So let's talk about what that means. So here I have this switch, 6 interfaces all connected. What's really powerful about a switch is that it helps break out each device into its own collision domain is what they call it, where if I'm sending from B to B prime, that does not interfere with communication from A to A prime. Those can be happening in parallel, concurrently at the same time without causing any problems. Okay. But what I can't do, because this defies laws of physics, is to say, oh, let me have A to A prime transmitting, but also C to A prime. Yeah, because now there's collisions happening because two people are trying to send to A prime at once, and then it has to use CSMA. It has to kind of make sure that those packets aren't colliding with each other. But between orthogonal or kind of different links, they have no impact on each other, technically speaking. So that's the really nice benefit of switches. They really help isolate out these different network or different links between communication. So how do you, if you you have A prime, how do they know they're reachable from these different interfaces? So let's talk about that. And what they do is they have a switch table, very similar to a forwarding table. It will keep that mapping of, okay, this data came from A, so now I know which interface to pass it off to. So let's go through an example. And how it does it? It just learns it. So unlike router, its forwarding table, how does it learn how to set the interfaces and IP addresses? Asks? Asks who or what? Not quite.
Don't hosts have to send something to the router first?
No, not quite. Routing protocols, right? Dijkstra's and all that stuff. State vector. That's how it knows.
Transmits its own data and then it receives the data from the other routers on the network next to it.
Yeah, I guess I would be careful. Data like control messages, maybe. That's how we meant by data. Sorry, maybe that's what you meant too. Yeah, control messages. So yeah, they will send control messages each other to figure out the weights and the costs. And so there's a whole set of algorithms that are dedicated to that, right? That we talked about. We spent a whole lecture. In this case, it's much more simple because it's only dealing with one hop. So it can just learn on its own. It doesn't need some kind of global routing protocol to help infer what it should be. So I have A, I want to send A prime. So what I do is I just send it, and the router, or the switch says, oh, wait, this came from A prime. Okay, now I've learned, or A. So now I've learned that A is hooked up to interface 1. So it will now keep that mapping because it received that packet from there. Of course, it has a time to live because devices can move around. What if you unplug from your one Ethernet cable and plug into a different one or something like that, And of course, we can't just say A is only a interface 1 because there could be other switches upstream. So there could actually be lots of devices that are connected to interface 1. So we have to just have this general table. But I don't know where A prime is. That's not on my table. So the first thing I do, if this thing's not on my table, oh, sorry, that's okay. Here's the algorithm for it, but we don't have time. Oh, class is over, right? Crap. Okay, is it sends that and then it broadcasts it out. So I don't know where A prime is, so let me just send it out on all my interfaces. And then hopefully someone responds, and when they respond, they say, okay, now I can put an entry for A prime, it came from 4, and now I have that mapping. So if I ever receive between those two, I know not to have to rebroadcast, not waste everyone's time. It only sends between 1 and 4, because it's learned for up to that time to live. Okay, router switches, here's that. All done. Okay. Great job. Thanks for being here, guys. It's like a couple days before Thanksgiving. You are dedicated. Yeah. I do have office hours. I'd be happy to go over the test with people. I'm also happy to go over the test other weeks when you maybe are more not anxious to leave. But have a good Thanksgiving. Travel safe if you're going somewhere. Eat lots of turkey and ice cream. Okay? Turkey ice cream. Okay. I'll see you all later.